Super. So I'm chairing, if you like, with Dimitro, and I'm chairing this second session. And it's my great pleasure to introduce Rafael Prieto-Curiel. And Rafael is a postdoc at the Vienna Complexity Science Hub. Before that, he was at the Mathematics Institute at Oxford University and also the Center for Advanced Spatial Analysis, London. And before that, very interestingly, Rafael was actually part of the police. He was the director of strategic analysis at the Emergency Attention Center of Mexico City, where he worked on crime forecasting and police and resource allocation. So at the moment, he's working on spatial analysis of urban development, I call it. But that's, I leave that to Rafael to really explain to you what he's working on. And yes, please, Rafael, I'm looking forward to your presentation.
Thank you very much, Caroline, for the nice introduction. And I want to say, as my first words, thank you, Yuri, Oksana, Mariana, and for the team that is making this possible. Really, my thoughts and prayers. And I know that this is just not something that we can easily say, but the example that you're giving us as the endurance and the capacity and the provisions to keep this alive, even under the tough periods that you're living, I think is something that we all admire and appreciate. So thank you very much for keeping this and keeping these Ising lectures after 25 years. So it's nice that you are keeping this memory. And thank you really for having me here. It's for me an honor. And I'm going to be talking about cities and cities in Africa mainly. And I'm actually very happy that I'm speaking right after Mark, because he introduced like the stochastic part, the random part, the physics, like the hardcore physics models. And I'm going to be talking about more like Africa and data and some of the challenges. So I hope you can see my screen now. And I'm going to be presenting something I call the scaling model for the morphology. So I'm going to be looking at the form of cities in Africa. And it's a scaling, because if you know anything about cities, and if you have been involved in cities, I noticed Yuri asked this question before, is that we know for a fact that cities vary too much in size, and that for many things is super interesting to observe, like these sublinear behaviors and superlinears, and you have like very dominating powers, but also you have very challenging aspects, because most of the, I would say, regular techniques that you would use for data, they don't apply in cities, because cities, they are very, very large sometimes, but they are rare, so fat tail, right? In the presentation, by the way, you will always see a flag of Ukraine in the intro slides, but also photos of cities in Africa. And I do that just to keep showing people that this is how Africa is looking now. Don't have the image of rural Africa with people moving from town to town. No, no. This is actually Dar es Salaam in Tanzania. And you will keep seeing these photos of very big cities in Africa. And just for the recollection, why am I looking at Africa? I started working during my PhD in the OECD as a consultant. And in the OECD is this big consortium, is like the UN. And they have different chapters. One of them is called West Africa. So one of the chapters from the OECD, that is West Africa, they want to analyze cities and terrorism and crime and displacements and water and resources and all these sort of different issues related to West Africa, particularly from Senegal to Cameroon. And I started getting more into the research of Africa. And let me show you here just something. I know that this data is not even the most scientifically valid or most detailed analysis, but I took 3 cities from Africa, Accra, Nairobi, and Cairo. And I measured here in the horizontal axis time between 1983 up until last year. And in the vertical axis is how many scopus, so academic documents we have related to Cairo. And you can see that it's becoming more and more relevant to do research related to Africa because this is increasing, right? And you see more papers related to Nairobi and more papers related to Accra. However, this is 1 year of London. So don't get the image that we know anything about Africa. Actually, what I keep saying is we know nothing about Africa. 1 year of papers in London is basically everything that we know for Africa, at least from the scientific point of view. I keep insisting when you do urban systems, like we want more London papers, sure, but we want many more papers about other cities, and that also includes Africa. So I keep pushing, like we need to decolonize science also in the objects of where we're doing this science. So when I actually remove London from this graph, you see, well, basically it's very limited our knowledge. And why I think it's relevant is not just decolonizing, it's not just keeping the diversity and all these beautiful things, but it's also a super relevant aspect that is going to happen in the next 30 years, is that cities, as we saw from Mark's presentation, there's two processes that happen in these cities, right? One is migration from rural areas to countryside, from rural to cities, they call it urbanization. So people are moving into cities, and you have something called population growth. So Africa actually at the moment is experiencing those two processes. At the same time, it's experiencing a very huge urbanization and a very huge population growth. Whereas on the opposite side of the spectrum, in Europe, we no longer have urbanization, so everybody that moved to the cities is already there. There's cross flows, as Mark was showing us, but basically that's it. Cities are basically on the final stage. And population growth in Europe is also almost close to zero. So in the next 30 years, Austria, where I'm at the moment, will have basically the same population as it has today. So 30 years is going to be roughly stable with a slight increase and decrease, but that's it. That means the size of Austria is fixed. And as Mark mentioned, the size of the largest city is proportional or of an order of the size of the country. That means Vienna is also roughly in its final stage, in its final size, right? So the size, the population, and the shape of Vienna, we basically finished it as humanity. That's it. There's going to be, and our estimate is maybe 30, 40,000 extra people in Vienna in the next 10 years, and that's it. So the challenge is, okay, how to make this sustainable, how to prevail these conditions. But the opposite side is happening in Africa. So in Africa, because we have urbanization and we have population growth, the size of African countries is increasing drastically, like really, really fast. And that means also the size of its cities. So let me show you just a few countries. It's always in blue, the size of that country in 2020. And in gray, you will see the size of the country 60 years later, in 2080, right? Ghana, it used to be 31 million people in 2020, and it's going to be 71 million people. So it's going to more than double its population by 2080. Remember, I said Austria is not going to increase, Serbia is decreasing, Hungary is decreasing, Italy is decreasing. So actually, Europe is already experiencing some population contraction. Here I'm showing you the opposite side. Ghana is more than doubling its population. Niger, in the next 60 years, is going to multiply its population by 5 times more population in just a period of 60 years. Mozambique is going to increase its population by 3 times by 2080. Kenya is going to double its population by 2080. And basically, it doesn't matter which country you choose, except for some of the Mediterranean countries. For the rest, you will observe this trend. That is, in the next few years, where the drastic changes are going to happen is in Africa. No longer is Europe. And to be honest, I'm from Latin America, no longer in Mexico either. In Mexico City, my city, we are 22 million people at the moment, and we're going to reach, in its biggest size possible, 24 million people. So it's almost finished. We're getting there till the last, we have just the last mile to run as a city, but not in Africa. And that's why, just because of the size and the explosion that we will see, and we will see it in the fastest period possible, this is one of the things I'm super interested in looking at African cities. What Europe did in hundreds of years of urbanization, North America did in 200 years of urbanization, Africa is going to do it in 30 years of urbanization. So it's going to be the fastest urbanization process in the history. And for that, obviously, we need some data, right? So let me show you. And I know that doing research in Africa is challenging. And I know because I've been there for quite a lot of time. And let me show you first a few data sets that I think are very useful for conducting academic research or policy research or trying to understand the processes in the cities. The first is Africapolis. And Africapolis is a data set produced by the OECD. It's open access, is public, is official, I say. It allows you to understand cities in Africa. It has for every single urban agglomeration. And if you have at some point analyzed cities in your life, you know that one of the first challenges is to define cities, because what is a city? Where does it finish? Who decided that London finishes here and the rest we don't call it London, or that Paris only has this or that? If you ask different people, you get different definitions, and their answers are extremely different. So if you Google Paris, some people say 2 million and some people say 12 million. So that change, that is just multiplying by 6 the population, that cannot happen in Africa, right? So the first data set is Africapolis, and this is the definition I will use for cities, and it's based on proximity of infrastructure. If you have a polygon and something is constructed within 200 meters of that polygon, you consider it to be part of the same city, okay? In Africapolis, we have polygons like this, are the geographical drawing of the urban polygon of every single city in Africa, more than 9,000 at the moment. And the smallest city or urban agglomeration has 10,000 people. The largest, Cairo, 22 million people. This, at least because you have the GIS data, you can intersect with other data sets, count, look at the SIPS flow, these distributions, and so on. And actually, something quite interesting is that I think it's one of the first times we're observing Africa. So I oftentimes look at papers that claim universal stuff, universal scaling, universal decrease of areas, universal. And guess what? It's not observed in Africa, obviously. So universal apparently applies to the US or some cities in Europe, but actually besides that, it's not universal at all. So I always go to the physicist and it's like, no, universal, I trust that there's more continents than North America and Europe, right? Anyway, so you have this data set to actually analyze the borders and of the cities. It's very fractal and it's using the same definition. It's backed up by the Austrian Development Corporation, the OECD, USA. It was super expensive because it's analyzing like thousands of cities, but you can download it and use it. It's very cool. Then a second one I wanted to show you is the highways, because analyzing the highways tells you like how do you move between cities, between urban areas or the rural part or so on. We took OpenStreetMaps data, we connected all the cities to Africapolis, so it's integrated. And if you want to do some analysis related to, I don't know, degree and connectivity, betweenness, and so on, you can use this data set. It's super tricky, especially in Africa, and because of how the data is collected from OpenStreetMaps. Because it's crowdsourced, a person was moving between one point and the other. So in the data set, you have this sort of issue that a person was moving from here to here, and you can see maybe on the tiny screen that there is one highway that is mapped between 1 and 2 points, but then there's a hole, and then the highway continues. And those holes, I mean, clearly in this map, you can see that it's connected, right? Or it should be connected. It makes sense that it's connected because otherwise, how do you get from the capital, Antananarivo, to the east of Madagascar if there isn't a big highway there? So maybe it's connected, right? The issue is that at the continental level, it's super tricky to manipulate, but we did it. It took like 6 months of work. This was one of the longest things I thought for networks. It took so long just to process this data, but to connect and to get a homogeneous definition of how the network should be. And this, what I did is input the segments that you have in the center. So, okay, you have Antananarivo, and you need to add segments of the network that are not there. With some rule, these segments are in total very small, just to keep a connected network, and that you can actually analyze stuff like a CT degree. So the CT degree, if you know something about networks, the degree of a node is the number of edges that are connected. Here, the degree of Antananarivo is 3. The degree of Antisaranana is only 1. The degree turned out to be super interesting just to observe many relations between mobility, centrality in the network, even the income of a country and the average degree of its cities. So there are many things to do with this network. And it looks like this, the network, once it's completed with the 2,000 cities with all the highways. But it's not actually mathematically now so complicated because it's not millions of data points, actually just thousands of cities and thousands of edges connecting with the biggest capitals, as I've been mentioning, right? You can ask for the nodes and the ledgers. They are in a public repository. They are open access. There's many interesting things to do with that network. But finally, let me get to the shape of cities, right? So that's what I wanted to get, and it's to analyze what is the shape of city. And now this on the background, by the way, is Luanda, one of the largest cities in the southern part of Africa, with around 10 million people. And as you see, like the cities are actually growing quite vertical. And what we wanted to get with our colleagues from the OECD is what is the outline of the future cities? What is going to happen with these cities? And why the question? Well, because as I mentioned, we know the population forecasts for many countries, right? And this population forecast is we're going to have in Niger 6 times more population. We're going to have in Senegal 4 times more population. So we're going to have cities that are super big. How are they going to be? So the current forecast is that Lagos in Nigeria could have something between 65 and perhaps 85 or perhaps even 100 million inhabitants. That means, imagine a city, a single city, that is going to be inside the population of the whole Germany today. And if not Germany, at least Italy or France. So that is a challenge. How is it going to look if we have a city with 65 or 100 million people? How the commuting distance is going to be? Because the first thing I imagine, obviously, when I hear 65 million people is where are you going to live? And where are you going to work? And what's the distance going to be? Because cities, they grow, and then, well, what's the footprint of that city, right? So the way that we characterize that process is trying to look at the footprint of the city. And we said, okay, a city can be round and compact if, like, you draw the outline of the city, and it's basically a rounded shape. Okay, it's not going to be perfect because nobody's that perfect, but if it's roughly rounded. But then if you have more space between things, more space between its buildings, then you can only be round, but not really compact. So we call this sprawl. You can actually be very tight things to each other, but not round, so more like a chorizo, elongated. Or you can have none of those properties, right? And what we did is we take the buildings of a city, the footprint of the building of a city, every single building that has been constructed in Africa, that is more than 300 million buildings. We intersected with Africa Polis, and I can tell you now what is the shape of those buildings. So what are these buildings located inside each one of the cities in Africa? So roughly we have 200 million buildings in around 10,000 cities. And the shapes that we're looking at, they look something like that. So imagine one building looks like this. Obviously, buildings tend to be square. I just drew them round because I like round shapes. But you have like buildings next to other buildings, and we can measure different aspects of these buildings and their distribution. What do we measure? One of them is the diameter of the city. The diameter is take one extreme of the building and the other possible extreme, and that we define as the diameter of a city. That means from every pair of buildings, every possible pair of buildings in a city, compute its distance and keep the maximum, and that you call it the diameter, right? It's very simple. This diameter is in kilometers. Bigger cities tend to have a bigger diameter. Then we computed also the average. So you take every pair of buildings, random pair of buildings, you repeat it thousands of times, and you take the average of those distances, right? And we have the number of buildings, we have the average area of all the buildings, and now we want to do some mathematics to understand what is the shape of these cities. Remember, the challenge when you observe cities is that the size of a city varies too much. So you can have a city that is too big, a city that is too small, and you call both of those things cities. So we wanted to create some indicator of a city that is not dependent on population, so that you don't always, just because of the shape, you say, oh, large cities tend to be bigger. Yeah, that's not informative, right? You need to discount the size. So for us, the cities actually look like this. Now you see actually one city, Accra, in Ghana, with all the Google Artificial Intelligence buildings located there. This is just one part of the city center. And you see all the polygon buildings that we have. Most of them are actually super small, and I will come to the size of buildings in a second. Some of them are actually quite big. Most of them are aligned, and there are many things related to the orientation of the streets and how there's like some cities that are always oriented north-south, or at least the same type of orientation. And basically that is the data that we have for every single building in like 6,000 cities in total, okay? There was some filtering here where some cities, they are not perfectly aligned with these buildings, so we had to filter them out. Google Artificial Intelligence is looking at images and contrast of images, so they are more confident when the contrast between the terrain and the building is higher. So if the building's materials are white and the ground is dark, then you have high confidence in this building. But when they use in the sand, for instance, same colorimetry, then it's not super confident. So there are some issues here with the data, but not really super interesting. If we put all these buildings together, we have 10,000 square meters, 10,000 square kilometers, sorry. So the size of Cyprus or something like that. So in total, it's quite an interesting data set. And by the way, it's again open access. And if you want, you can download from our repository the intersection between polygons, urban areas, and these buildings. So you don't even have to do the sort of intersection that could take hours. And now for the mathematics, I'm a mathematician, and I really love these sort of questions. So imagine you have a circle with an area A, right? And you take two random points inside that circle. What is the expected distance between those 2 points? I didn't know the answer, and it actually was like my Christmas puzzle. I was thinking, what is the average distance between any 2 points inside a circle of an area fixed area A? And it turns out that there is this beautiful formula, and I really love this formula because the average distance between any 2 points that you take inside a circle is 128 divided by 45 pi times the square root of the area. Now, this 128 divided by 45 pi is a math formula that humanity has known for like a few decades. I love this super exotic formula because this appears in the paper as well. The square root of A is just the radius, right? By the way, if you do the calculation, 128 divided by 45 pi is almost 0.9. And this formula is just basically telling you that the average distance between two random points inside a circle, okay, you can take the two extremes, or you can take 2 points that are in the center, but the average that you will get from that distribution is 0.9 times the radius. Okay? Cool, beautiful formula. Now, what about the average distance between 2 points inside an ellipse, right? Because cities are not going to be circles, cities are going to be more elliptical. And maybe in the ellipse, I can define something like the elongation or something like the eccentricity of an ellipse. So if you remember your geometry lessons from like a few years ago, an ellipse has the eccentricity, and we can actually use the eccentricity to measure how elliptical things are. So if the eccentricity, I think, is 1, then you have a circle, and if it's smaller, then you have a more elongated shape or something like that. So you have in an ellipse the small axis and the big axis. The big axis I can measure, again, if I go back to my buildings, is the diameter of the city. So that's why we wanted to measure how elliptical it is, the city, based on this city diameter. And it so happens that the average distance between 2 points inside an ellipse doesn't have a closed formula. Or if it does, it's like 3 pages long. So not super beautiful, but no worries, we can approximate it with some formula. And that's what we did, taking basically as an idea that the average distance between 2 points inside a circle is 128 divided by 45 pi times the square root of the area of the circle. We use that formula, but now inside an ellipse, right? And now inside an ellipse, what we do is we take the big axis and the small axis, we take those two, and we modify it to look at the average distance between two buildings inside the city. So that's where the formula was born. The average distance between two buildings inside the city, that's the left-hand side, is 128 divided by 45 pi, so the same exotic numbers, times the square root of, and for the circle was just the area of the circle. Here for the ellipse, I have 4 multiplicative numbers. One is the number of buildings inside that city. Well, that's where the B comes, but that I can count because that's just the data set that we have. Multiplied by the average size of the buildings. So the average size is I take all the buildings inside the city and I take what's on average that number, right? On average, a city has buildings that are like 20 square meters. Then I multiply that by a coefficient that measures the sprawl. Sprawl is how open or close is this city. This coefficient is almost always 1. And if it's slightly above 1, it means more open. And if it's smaller than 1, it means super compact. And then multiply by the elongation of a city. The elongation, if you have elongation equals to 1, is a circle. And if you have a bigger elongation, more and more and more and more elliptical. So with these 4 multiplicative event coefficients, we get the base model for a city. And I thought it was cool to call it the base model for a city because at least you have a name for starters, right? That's why we thought a lot to have BASE. And that's the average distance between two buildings inside a city. That again, that I can measure. So this distance is measurable, is buildings that I can measure, the area that I can measure, and these two things that I can create a formula for them, right? What is interesting is that based on this, now we get the elongation and the sprawl of a city. So I can do some algebra and say, okay, the sprawl of a city is 45 pi times the distance in between a city divided by the square root, blah, blah, blah. So some algebra here and gives you the sprawl and the elongation of a city, right? How does it look? Well, we call from the formula inside the circle, the formula in cities is basically the same, just is the footprint, because if you multiply 100 buildings, that's the number B, times the average area that they have, that's everything that has been constructed in that city. That's the footprint of the city. And then we multiply by 2 coefficients, S and E, shape and elongation. And you have then two multiplicative components. The footprint of a city, that's how many meters have been constructed, times the morphology of a city, right? This morphology, and this, I know that it's been a bit exotic talk, but the morphology coefficient does not depend on city size. So you here can very easily say, I can compare the elongation between Lagos with 20 million people and Kumasi with only 1 million people. And it's not going to depend on the fact that they are bigger, because this is not, by construct, is not dependent on size, right? In essence, what we want to get is the sprawl and elongation, because that's the form of a city. How does it look? Let me show you this figure. And I think if you get this figure, then the rest of the formulas is really just the exotic way how to get them. So here I have 9 cities in Africa where they are basically the same size. So I wanted to convince you that size is not the relevant factor, right? Kaduna with 1.4 million people, Embu with 2 million people, Aba with 1.7. So they are big cities, but they are not super big. It's not Lagos, it's not Luanda, it's not Johannesburg, it's not Cairo. So I have the big but smallish big cities, basically the same size. Every building that I encounter in that city, I plot it with a super tiny dot. So if you zoom in a lot, you will see here tiny, tiny dots that represent the buildings in Kigali, all in green, or the buildings in Brazzaville, all in red, right? And they are plotted to the same scale. So I don't move, and I just see without changing the zoom I am taking on Google Earth, for instance, I plot all the buildings from Kaduna and all the buildings in Kigali. In the horizontal axis is the elongation of a city. And remember, it measures how chorizo it looks like. So more to the right, it's more like a chorizo. More to the left, it's actually like a perfect circle. And now you can see it. In Kaduna, well, the city is not a perfect circle, but it is very like rounded, right? Especially compared to Kigali. Look at Kigali, how there's branches and the city has to accommodate to the physical terrain because Kigali is surrounded by lakes. So it's very sinuous the way Kigali has evolved to that shape, right? In the vertical axis, we have the sprawl. In the bottom is buildings that are super compacted and close to each other. And the more you go to the top, then they open up like a beautiful flower. But the issue with the beautiful flower is that really is a more pollutant flower. Let's be honest, a city that has a higher sprawl, it means that you take longer for commute and that eventually you will require more energy for that. So Embu with 2 million and Brazzaville with 1.6 million, the difference in size is population-wise almost nothing. Form, drastic changes, right? So where would you like to be? Just in terms of urban form, in cities like Kaduna or Brazzaville, because commutings are easier. Because here in Embu, moving from one extreme of the city to the other, or in Hawassa from one extreme to the other, that is going to take you hours, right? And if it takes you hours today, now the challenge, how is it going to look like in 30 years when the population doubles? Because that's going to happen almost to every city in Africa, right? So we did the scaling analysis, and now is what Yuri, you were asking before, that is, what about the scaling and Geoffrey West's and these ideas of universal? Well, this is when I say like, well, universal applies for the US only, but okay. Here I have in the horizontal axis, the population of a city, from very small cities to very big cities, right? In red is Cairo, here in this red dot. And these two are Lagos, Onitsha, and other cities, Johannesburg in South Africa. And in the vertical axis, I have the number of buildings. That's very easy, right? The number of buildings and the city size, both axes are logarithmic. So then you have this sort of straight line. However, the coefficient that you get, as Geoffrey West, his scaling laws, the coefficient is not exactly 1. It's actually slightly less than 1. So it's slightly sublinear. I mean, slightly. it's tricky to define more sublinear. So it's just sublinear because the number of buildings in larger cities is slightly lower than a linear relationship. For every three persons in the city, you construct a new building. Basically, that's the rule that we observe. And that's this on the left-hand side, right? So the number of buildings, we can express it as population to the 0.981 with some constant, but to avoid that constant, we write this proportional fancy alpha, right? What about the area? And it's going to be, remember the base model is BASE. We started with buildings, more buildings in larger cities, but sublinear. It means fewer buildings if the city gets larger. Now, in terms of the area, something super interesting is that buildings get slightly larger. So this coefficient is not zero. Zero would be there is no impact, but it's not zero. That means larger cities tend to have bigger buildings on average. Remember that we look at the footprint only. And by looking at the footprint, we observe that buildings get more area-wise bigger in bigger cities. And in small cities, you get actually, on average, very, very small buildings. The sprawl is not zero, very close to zero, but it's not. So bigger cities get slightly bigger sprawl. And the same happens with elongation. Now here, a regional analysis makes it slightly better. That means if I take 6,000 cities and I put together everything, we observe this close to zero and close to zero. If I only observe a part of the continent, like say the southern part of Africa or West Africa, you get like very different coefficients. And some of them are quite interesting to observe because actually cities get more compact and more round as they grow. And that's what we wanted to get, right? So we express buildings, area, surface, and elongation as a function of the population. And if you remember, we obtained that the distance the average distance between buildings is 128 divided by 45 pi times the square root of, and the square root is just putting all of these things inside the square root, right? That square root, I can just write the population to the coefficients that I have, 0.11, 0.05, but the square root divides this by 2. So what you get in this formula is that the average distance between two buildings inside a city grows according to the population to the 0.532. And this 532 is slightly bigger than 0.5, right? So the distances grow faster than the square root of the population. That means actually something very critical. We grow in distance bigger than if we just put together people using each person 10 square meters. So one way we could think of a city is start from the center and think of a disk of 10 square meters for each person. And if you just keep adding disks, the average distance between two of them should grow population to the 0.5. But in Africa, with 6,000 cities, we observe that distances actually grow slightly bigger. What is the main contributor? Obviously, more buildings. That's obvious, is 0.98. But if you discount buildings, the next thing is that buildings get bigger. So why are distances larger in bigger cities? Because buildings are bigger. And a slight contributor because there's a slightly more sprawl and slightly more elongation, right? Why do we care for the average distance between buildings? Because that's basically a commute. That's basically how much energy the city is going to require for moving, right? So we take the distribution, and if on average you have to visit one of your colleagues or friends, you would take on average this distance. Now, let me go to the city center because I know, and this is a severe critique, that it depends too much on how you define a city, right? So if you define a city with very fractal edges, then maybe you put one in the extreme and one on the other extreme, and this is very sensitive. So let's remove that factor by looking only at the city center. By looking at the city center, I take the most dense point of the city, I open a radius of 1 kilometer and I observe only that as a unit. This doesn't depend on shape, right? Because they are all circles and they are all 1 kilometer. So this should be an interesting way. So we have this same 1 kilometer disk for cities like Accra or Bangui that are, if you notice, super constructed, super high in density. For cities like Perere or Seviu, medium constructed, not super much. Or even in cities like Ngalango or Kibande, there's almost nothing constructed there, right? So what we analyze is what has been constructed inside this circle of 1 kilometer, and we call it the percentage of the footprint of 1 kilometer. And again, let's look at the scaling relationship. We put the population in the horizontal axis, and we look at how much has been constructed in the vertical axis. This doesn't depend on the size, because I took 1 kilometer. This doesn't depend on the form, because I just crop down the circle and I take only that circle. And what you can see is clearly a very strong relation. That means, basically, yes, analyzing footprint is tricky. Analyzing the shape of a city was complicated. You have super exotic shapes that depend on how it was drawn, that depend on contiguity, but okay, let's look only at the center. And if we observe only at the center, we actually get quite a big impression of how cities are and what cities need to do. Construct dense and vertical is one of the key elements for sustainability. And by vertical, I don't mean Abu Dhabi, Dubai sort of buildings. It's just more than one floor. Because the next thing is we look at the building size. How big are the buildings in the dataset? And I know this figure looks super weird, but for each one of these lines is representing one of the cities. And we have 5,600 of them. And in the horizontal axis, I have the building surface. And the line represents the number of buildings larger than that quantity. So for instance, here, this point that I think you can see on the screen, it tells you that around 90% of the buildings in this city are bigger than 20 square meters. 20 square meters basically is a room 4x4 or 4x5, right? A room 4x5 tells you here that in this city, 90% of its buildings are larger than that. A city that is in the bottom, it tells you that here, only 15% of its buildings, are larger than 20 square meters. That means 85% are smaller than 20 square meters. Most of the buildings in this city are too small. So small that are smaller than a room, basically. And okay, we don't have the height of buildings, not at the moment. We are working with our colleagues from the German Aerospatial Agency to get the height of buildings. But even without looking at the height of buildings, in a room that is only 20 square meters, what is the height of that building? Well, one floor. You cannot build, maybe two, but that's it, right? So we get a very good idea on what's the volume and the volume per person in these cities, because the average size of buildings was too small to analyze. Now, if I move a bit to the right, in this dashed line with 100 square meters, now 100 square meters, this is larger, right? That's a 10 by 10, 10 meters on one side and 10 meters on the other. Buildings that are super large, they are present in Africa, and I've been showing you photos with actually skyscrapers and very big buildings. And some cities actually are quite dominant. So for instance, in this one, buildings, more than half of its buildings are super large. What is the advantage of super large buildings? That bigger footprint enables to build taller, and that reduces the necessity for more materials and for longer distances. Usually, if you don't pile up like a sandwich, you just put it next to each other, increasing the commuting distances, right? What is something super interesting is the characteristic of building size. Is correlated to the income of a country. For instance, here you can see in red how would be the line of Accra, and in blue what is the corresponding line for Bangui. The difference is that Accra is one of the rich capitals of West Africa, the capital of Ghana. Bangui is, I would say, one of the poor capitals in Central African Republic. So in Bangui, the number of buildings that are big is actually super small. So you encounter a dominance of very small buildings in Bangui and not so much in Accra. And if I highlight here the buildings, for instance, in Johannesburg or in Addis Ababa, you will see that in big, richer capitals, there is a dominance of bigger buildings. So they actually do get better. They get taller, and space gets too valuable. So you want to use it as much as possible, and that's why cities go vertical. Finally, I know that I need to wrap up very soon. Let me show you some ideas of what is the scenario, because what the OECD wanted to ask us is, what is going to happen when the cities grow? Because that's the current situation, and the current situation is just a snapshot, right? But what will happen when the city doubles its population? And I stand from the position that at the moment, every city in Africa will double its population, right? Maybe not. Maybe Mark here has a model that explains better why not. But let's analyze the footprint today, the shape today, the everything today, and let's double the population. The time frame for this to happen is not the same. In countries like Senegal, it's going to take longer. In countries like Niger, before 2040, they should already double the population. So in the next 20 years, it's going to double its population. And we came up with these three scenarios. The current is if a city stays where they are in terms of shape. Just you pile up more buildings, you keep constructing with the same elongation coefficient and the same sprawl coefficient. Or best, we can just take one of the best scenarios for elongation and sprawl in your region and actually consider that the coefficient that you will grow. Or worst, obviously, just to show what is the relevance of this. So when a city doubles the population, and here I have the three scenarios, the current projection that we have is that when a city doubles the population, the average distances, and I measure the impact in terms of average distance in the country, in the city, because the average distance for me is going to be pollute, right? It's going to be energy, it's going to be the commuting time between origin and destination. So when the city doubles the population, because of the circle, because of the compactness and the sprawl of a city, the distance in the city should increase times 1.45. If we plan and if we actually get a better sense of how to use space better, we grow cities more vertically with a better use of materials instead of just expanding horizontally, because that's the easier and cheaper way to construct. Distances will increase by 27%. In the worst case scenario, that is just a non-controlled growth horizontal, is going to increase 61% the distances, right? But now, some mathematics, and this is too simple. What is the impact? Well, for me, the energy that a city requires for commute is the distance traveled, and here I'm showing you the impact of the distance, times the population that needs to travel those distances. Because it's not the same if 100 people need to travel this distance to 1,000 or 1 million. So this larger distance, 45% bigger distances, is traveled by even bigger populations. So for me, the commuting energy, that means I ask for every city an estimate of the distance that they will travel times all the people that should travel that distance. In its current situation, the distance should increase times 2.9 times. The total energy, that means people traveling longer distances, well, yeah, it's double the people, right? So of course it's going to double or more the energy. But double the people traveling longer distances is almost 2.9 times the 2020 energy. again, if we do something good, and if we preserve and we conserve shape and we compact buildings and we reduce elongation, the total energy is going to increase only 2.5 times the 2020 situation. But again, in the worst case scenario, if the growth is not controlled, double the population is going to be 3.2 times the energy that they are consuming today. So it's relevant, and that is why we think that, okay, I know that is a super simple way of observing commuting distances, and we don't have a modal share. That means we don't know if the person is moving by car or if they're moving by bike or if they were walking. But still, as an aggregate, what we are looking at is how more people travel longer distances, creating even bigger frictions or more time spent in commute. That is going to create, in the scenario of a 3.21, very complicated situation, especially for cities that are too long or too big. And I mean, here, if you're interested, we published policy paper with the OECD on the impact of this, the relation to urban forms, and the green urban areas, because green urban areas is a critical part now, and our paper on the scaling of the morphology of African cities. So if you're interested, you can look at that. Also, I would be super happy to answer questions. But let me just, before I finish, also show you another couple of articles related to African urban forms, related to the dynamics of urbanizations, to the scaling of cities, to the interurban areas, to the travel between cities. Like, I do think that Africa has a lot of interest and also a lot of academic interest, because there are this many like questions to look at and novel data to analyze. So even, for instance, looking at the cities and its relation with other cities. So anyway, I hope that with this, I convince you that Africa is an interesting place to observe, and I would be super happy to take any questions if there are any.
Fantastic. Thank you very much, Rafael, for a really interesting talk. I open the floor for questions, comments. Anyone who would like to go first? Maybe while people are still thinking about it.
I see Mark has
there's
rose on
someone.
his hand.
Is that, I'm just getting my head around this. Is this Mark, yes?
Right.
So please, go ahead.
Okay, thank you. Can you hear me?
Yeah, we can hear you well.
Thank you, Rafael, for the nice talk. I saw your paper a little bit. Can you just indicate where, if there are any interesting open sources on African cities, some data about African cities? What would be, for a newcomer, where should we look at? Do you know that? What would you advise?
Definitely. For me, the starting point should be African cities is Africapolis. Is a table with 10,000 rows, one for each city, with unique identifiers for each urban area. So it's already an agglomeration with population forecasts between 1950, backcast to 2040, sorry, 2030 is at the moment. And separate to this data set, but in the same website, that is here, Africapolis, you can download the GIS polygons. Depending on the interest, working with the polygons could be slightly challenging, and especially if you don't have the right software or if you're not used with these packages in R or in Python that open the polygons. But for me, those two, that at least you have a table for all the African cities with a coherent definition for cities. And the polygon, that is an interesting starting point to look at, because you have the same definition from Senegal to Ethiopia and from Egypt to South Africa. But if there are more sources, I have a link on my website to all the repositories I have created. One for all the highways, one for all the buildings, one for the urban metrics, And there's also ACLED. I'm not sure if you're familiar with ACLED, but ACLED is a fantastic website that gives you all the politically motivated violence from the year 2000 up until today, and is geolocated. So if you want to analyze, for instance, terrorism in West Africa, violent events in Nigeria, protests in Somalia, ACLED is a super interesting database, also open access. If you want, I will put a link in my website as well.
Okay.
And what you can do with that really is analyze urban violence, urban protests, demonstrations, the flow of people and how they react with an increase in terrorism. All of these data are open access and now easy to work with, I hope.
Okay, great, thank you. Because I saw that on the World Bank, for example, and places like that, but the data is scattered. I looked for some, data about access to water or waste management, etc. But I found that the data was very scattered in here and there, and I couldn't really get, I wasn't super happy with what I got. So I will check the site you're recommending. Thank you.
Thank you, Mark. Actually, I agree with you. Looking at aspects such as water sources or accessibilities or data points is actually super tricky. There is no integrated project that looks at that in a cohesive way. I have seen a few papers, and maybe you have seen them as well, that they look at OpenStreetMap's data. They intersect points of interest in the polygons, and they say, well, water fountains or markets in the city. The issue is that because it's open access data, open maps data, it depends too much on how it was captured. And what we discovered is that you have countries, full countries without a single market. But that's wrong, right? That's just because the data is not capturing, not because there isn't a single market in the city. Or countries where you only have all the churches and temples marked as points of interest. So tricky to work, and I agree with you that the next step for analyzing cities in Africa has to be these sort of data that the World Bank has one, but the OECD has one, but there's one for the mobility, integrate them into a single project. Yeah, I agree.
Thank you.
Any other questions or comments? Yes, Yuri, you come.
Yeah, thank you very much. Very interesting talk. I have a question and I have a comment. The question is the following. Did you try to make analysis of your data with respect, for example, to, you are speaking about shape, and in the former lecture we had growth of cities and shape of percolation cluster and shape of DLA cluster in 2D. So did you try to measure fractal dimensionality of different cities? And what would be an outcome? One, and the related thing, another technique, for example, if you consider the network of buildings in the city. So obviously it will be the spatial network, right? And then you can continue comparing networks of different cities between them. And then I say my comment afterwards. Yeah.
Excellent. Thank you, Yuri. Super interesting questions, both. We tried to define the network, the spatial network. We didn't actually finish that segment because we were at first on this project, we were trying to look either at network of the buildings and I was telling them like, no, I think with average distance, we can actually model most of the process. So I convinced them to move to the average distance rather than the network. But I see the power of that analysis, and we are actually at the moment applying for a grant to try to compare cities. The issue is that I have a snapshot and I don't have like a video, right? I only have a photography of cities, how they look. And I would like to see how they evolve, because usually a city, you keep adding stuff nearby or you keep in building in the center. any of those two processes that would be super interesting to observe, we don't have the data because we just have one snapshot from Google Artificial Intelligence. The next steps for us is trying to look at cities in different moments of their urban trajectory. So a very early stage are cities in Africa, and very late stages are cities in Europe. So we know what's the terminal size of a city, say Vienna. This is nearly over, so we know how is it going to look like in the end of the story, and trying to look at the city in the early part of the story. So this is what we're trying to do at the moment on the moving the city. Otherwise, because our time frame is too short, we will observe 2020, and if we have data today, it's going to be 2022 or 2023. In 3 years, the city only evolves a bit, so it's tricky to say that this is the process of the dynamics. What we did actually is the cluster of cities. So
no, I was not about cluster. Excuse me, I was not about the process, but an outcome. For example, if I say DLA, I know that fractal dimension of DLA cluster in 2D has certain number. And then if I say percolation, I know that the percolating cluster in 2D has certain dimensionality. So in your case also, without process, just measuring fractal dimensionality.
Yeah. No, we didn't try the fractal dimensionality. I am familiar with Stefan Turner's and Roberto Molineiro's paper. They look at the 3D building, 3D cities, and they want to measure this fractal aspect. The thing we didn't have is height of buildings, and that data we didn't have, at least for Africa. What we did get is from the German Aerospatial Agency, the DLR, the height at the pixel level. So not per building, but like in this area, the height of buildings is this much, and the height of buildings is this much. We did observe a very clear relation between city and height, and something they are calling the pyramid cities. That is, in the center, buildings are bigger, and as you move out, they become flatter. Richer cities, they are usually richer, taller buildings, but not something really at the moment related to the fractality. So maybe next steps are along those directions.
Thank you.
And you had a comment.
Oh, yeah, that's
Sorry.
right. Jurgen, you had a comment also?
Yes, I do, but maybe I keep silence for the moment, allowing other people to speak, and then I say my comment later. Thank you.
Okay, we'll ask you again then. Rafael, I wanted to ask you about these different power laws that you showed, and a critical person could argue that, well, for some of these at least, these might be some form of fat tail distributions, but maybe not a power law, maybe something else. And even if it is a power law, I would expect some form of, you have it in your image, but you don't have it in the numbers, some form of error bar. So, and what is the impact if you change them slightly? So for example, if you maybe make the elongation exponent, if you make it negative, what happens then?
Definitely. Thank you, Caroline. So what I wanted to show in this is that it's not actually so obvious that this is a power law, precisely. Only in the case of buildings, you see that the stripe is actually very clear and linear, and this is it. So this is the only thing I would call universal, in the sense of like it applies for the US and Africa as well, universal. But for the rest, actually, it's not that obvious that there's a power law here. If you see this coefficient is close to 0, and the line is almost horizontal. So for me, it's not, it's a power law because you fit a power law. So you force the model in the statistical sense to have a power law, and therefore you obtain a coefficient.
Sure.
Yeah. The beauty part about the power law, and that's why I think for mathematicians, well, more physicists to be honest, is that you can then do this product of all the things that are related to the population, and then you obtain a single equation, depends on the population, right? What we did here is, instead of looking at a continent, let's try to look at the 5 regions of Africa. It's because in the universal paper that Jeffrey West published, he looks at 200 cities in the US, and that's universal in 200 cities. Since we have 6,000 here, let's divide in 5 subcontinents. Still, we're going to get more than 1,000 cities in each subcontinent. Still is bigger than Jeffrey West's sample size. And once you look at the regions, actually the power laws are much more clear. Especially, you observe like these regional differences, where North Africa is extremely different to the rest of the continent, where there are very big city developments in West Africa because there are many governments putting money into Lagos, into Accra, into Abidjan. So there are many big developments happening in West Africa, and those two are separate. Central Africa, challenging. Poverty is tricky, and there is no very big city. The biggest is actually not super big. So it does divide like the regions, and in the different regions you observe different aspects. In particular, in many regions you observe that the elongation has a negative coefficient. That means a small city is like a chorizo, and when the city grows, actually they do become rounder, and that's what we were expecting, that larger cities should become rounder because the space is more valuable and the space is more critical. So for me, I was always expecting bigger cities to be rounder. That means this coefficient to be negative. Sprawl should be negative as well. Yes, we have a better use of space, so it becomes more critical. You don't want to commute long, so therefore you start using whatever is available for you in the city center, increasing the sprawl. And once you look at the regions, it does look a bit negative. And with the OECD, what they want is precisely to create policies and to talk to mayors from Africa and convince them on how cities should grow. Now, looking at the different aspects of a city, right? There's no recipe for, okay, all the cities should follow this trajectory. Well, no, actually, we observe different typologies. We observe different clusters of cities, different materials, depending on the geographical conditions, on the materials nearby. And all of that to say, still, you should grow less sprawled, more compact, and less elongated, more round, to reduce the distance that you are forecasting to triple in the next 3 years.
Thank you. Thank you very much. Any other questions, comments?
If no, may I?
Please.
Yeah.
Please.
So the comment is the following. So some time ago we did some study in physics of soft matter, which might be, I think, very relevant to what you were speaking today. We were studying the shapes of complex polymers. So, and these are universal. So the story goes back to beginning of the century, to the paper of Kuhn, who put the question, you know, you have the random walk, and you look on the random walk from far away. What do you see? And it appears astonishingly that you don't see the globe, but you see something, as he wrote in his paper, as a bean, so elongated, although it is random walk. And this gave, so for some obvious reasons, and this gave the origin to studies of shape of self-avoiding walks, which are connected to the shapes of polymers in good solvents. Then we wanted to quantify it. So we used renormalization group theory to quantify it. And it appears that in soft matter theory, people have some standard way to quantify it. They calculate something which is named gyration tensor. So you should, basically you have polymer, many monomers, and you calculate gyration tensor for these many monomers, as you have many buildings. And then having it at hand, you calculate invariants, which give you asphericity, which give you opaqueness, which give you many standard observables. When you spoke here about compact, round, and so on, I understand you define them, but you define them empirically, phenomenologically. Whereas there, it is no doubt. It is just entire number. So we calculated these numbers for complex polymers. And now I think that this methodology can be one-to-one used. You have many, many dots, which are buildings. You calculate gyration tensor, and you calculate all these features. Moreover, when we did it, we learned that people are doing the same thing in astrophysics. You have many stars, or you have many galaxies, and you want to have a shape it. What they calculate there, they name Minkowski invariants. These Minkowski invariants can be traced back to our gyration tensor. Both are kind of perfectly defined in mathematics. And I am sure they are related to the features you were calculating here. And afterwards, I learned that there is a branch of mathematics. I'm sorry, but I was never aware about this branch, which is named integral geometry. I know differential geometry. I never knew about integral geometry, which has origin in geometric probability theory. So I think if you want, we can discuss more on this, but I have an idea that this methodology will be probably very useful in what you were speaking about. That's what I wanted to say.
Thank you very much, Yuri. Super interesting question. I will look for these concepts. They are definitely outside of my scope and outside of my knowledge sphere, I would say. But they seem super interesting and super applied to the challenge that we're looking at. It happened to me once, just because there's like a couple of minutes. So when I was doing my PhD, I was looking at crime, and most of what I did, my research was crime phenomena happening in different urban settings. Once I went to a conference about dust particles in the atmosphere, and I thought, well, I'm not going to understand much, but okay, right? I got there just because it's quite interesting. And slide number 2, and I'm like, whatever my colleague is doing is exactly the same model as I apply. Crime and those particles in the atmosphere, mathematically speaking, we map them, we use a kernel density, we try to obtain contour curves depending on some parameter. And I was so happy to observe that this is what happens with mathematics or physics or these quantitative sciences, that you can change the topic sometimes, but the tools, they come so powerful that we apply them to different settings, such as crime or those particles in the atmosphere. And here you're describing polymers and cities in Africa. And I love it. I think it is a super interesting way to analyze cities. Also with the challenge that really the smallest city in Africa has 10,000 people. The biggest city today has 22 million people. So because it changes so much, the challenge is to define something that doesn't depend so much just on the city size, right? But that was for me the biggest challenge. So I will look into this idea of the polymers and the gyration tensor.
We discuss more, but that's one of the reasons we make such a meetings. You know, when people from slightly different fields meet, that's always very interesting to discuss. Yeah, thank you.
It's beautiful. Yeah. Thank you very much.
Yeah, I agree. That comment was just beautifully connecting two areas where you think, wow, they have something to do with each other. Great, thank you. Thank you, Yuri, for sharing that. So in terms of time, we are sort of out of time, but if someone has a final question or comment to make, then there is a minute left. And if that is not the case, then I will just hand back to the organizers. I'd like to thank Rafael again for a very clear, very nice talk, everyone for their questions, and for listening, of course. And so, Oksana, Yuri, anyone who would like to?
Yeah, so I just add my thanks, and also I want to thank to both chairpersons of today, Carolina and Dmitro, and to both speakers, Mark and Rafael, for this very nice second day of our conference. And we are looking forward very much to meet you again tomorrow during the third day.
Again, thank you for inviting us, and thank you for keeping this conference alive. For me, it is very important, and it has been such a fantastic experience. And my thoughts and prayers with you and with the people from Ukraine and your families. See you in Zoom.
Thank you. Thanks so much.